Welcome back. Today we are going to continue on this kind of causal inference cautionary tale. And so I'm going to illustrate kind of some fun examples with conditional probability based on climate change. So let us dive in. So, based on a relatively recent YouGov survey asked to 1,600 folks from Great Britain and another 1,300 folks from the United States of randomly sampled adults, were asked the following question about the global environment and what best described their view. They were given these 4 options and had to indicate which matched their views best. Climate is changing and human activity is the main cause, or is mainly responsible. The climate is changing and human activity is partially responsible, together with other factors. 3, the climate is changing, but human activity is not responsible at all. And 4th, the climate is not changing. So, as we can kind of see here from the raw numbers, 800 plus people from Britain agreed that it was people's fault. 500 from the United States believed it was people's fault. 490. You can read the table. I don't need to read the table to you. You're all smart, capable, lovely human beings. So here's some raw numbers. Great. Raw numbers, nice. But we should really look at percentages because we're not comparing like to like. The total number differs. So we've just got about 3,000 people, but 1,600 of those are from Britain and 1,300 are from the United States. So we can't really compare the 500 to 800. So let's turn them into a percent. So the overall percent here is 45%. What we do is we take the total sum of endorsing that specific opinion and then comparing that to the total. So like $3,000. Now, this comparison differs when we look at the British versus the Americans. So here, more than half of Britons think it's humanity's fault that we're getting hotter because we're looking at 800 out of 1,600. While in the Americas, the US of A, less than 40%. Yay! Okay, so fun activities for you. You may be asking, why the hell am I doing this? I'm giving you a reminder about conditional probability because it comes up a lot and you'll see it but not realize that that's what's happening. So we can calculate those various percentages here because we assign those. And in all likelihood, there's very much a third variable explaining these relationships. Who knew? Americans, not a fan of climate change. Cool. So let's talk about some basic probability properties, just so you have them, and I have them too. So probabilities range from 0 to 1. The probability of the entire sampling space is 1. Probability of A or B is the equivalent of probability of A plus B if they're disjoint. That's not the same as them being independent, that A and B have 0 overlap whatsoever. Probability of not A is 1 minus probability of A. Bob's your uncle. Woo! So I have very detailed notes here, but if you need a refresher, please pause here. Sorry, I had to entertain myself. So that you can look at these because people forget. Here are those abridged properties again. All right, last one I'm going to talk about is conditional probability. So that's the probability of event A given event B. So P, open paren, A, full, like that tall line, and then B should be read as probability of A given B. So you can read it from left, right. Yes. Wow. Mason can do stats in her head. Yay. Okay. So if the probability of B depends on any sense of the probability of A, then we really need to talk about the conditional probability. So if you flip this, so you can also read this as, I just flipped the numbers. So let's just do an example. Let's just dive ahead. Okay, so weather. So the probability is B. The B is the event that John carries an umbrella. A is the weather forecast predicted rain. So if you combine them together, so if John is holding an umbrella, it's very probable that it's also about to rain. So these two are these are super linked. They're super conditional. We're almost to the point where the probability of A is the same as the probability of B given A, because they're that closely linked. So if we do cards, the probability of a king is 4 out of 52. The probability of a second card being a king, given the first card was a king, is 3 out of 51, because we've taken out of the subject space the odds of, we've taken out a king from both top and the bottom. Now, the probability that the second card is a king, given the first card's not a king, is 4 out of 51, because in that universe, we've drawn one card, but it's not a king, which means there are 4 left. Cool. Independence is the last one, I promise, because I lied the last time when I said that conditional probability. So 2 events are independent if the probability of A given A is the probability of blah, blah, blah. Cool. I might edit that out. Probably not. Let's back up. Okay, so 2 events are independent if the probability of A given B is the same as the probability of A, as well as the probability of B given A is B. 2 events are independent if knowing one tells us nothing about the probability of the other. Card example, probability of a heart is 13 out of 52. Probability of a heart given a jack is 1 in 4. They're independent because there are 4 cases for the jack. Here is independent, but this is not the same as disjointness. So if A and B are disjoint, then the fact that A can occur tells us that B can't. So they're very dependent. Cool. I realize that was a very strange meandering, but I promise it is relevant in the next video, because stuff like this comes up all the time. I'll see you later. Bye.